Okay, let me welcome you to this fifth lecture of our course on reinforcement learning. And the first four lectures were sort of overview lectures. They were designed to paint the big picture of the field. And then in the following lectures, we're going to go in greater depth in some of the some selected topics, particularly related to rollout and also to various types of neural network approximations as described in your class notes. So today we're going to revisit finite horizon dynamic programming problems and look at rollout, and particularly rollout for deterministic problems. So we're going to do some review of finite horizon problems, and then I'm going to discuss how they are related to infinite horizon problems, so that insights that we have already gotten, both algorithmic and also visualizations related to infinite horizon in the previous lectures, can be applied to the finite horizon problems that we're going to be examining. Then I'm going to talk about rollout in general, again, a review. Then I'm going to focus on deterministic finite state systems. Finite state because they facilitate the computations. And we're going to look at rollout within that context. Then we're going to look at the theoretical improvement property of rollout, namely that the rollout algorithm performs better than the base policy on which it relies. And then after we take a break, we're going to look at the variations and extensions of the deterministic rollout algorithm. So a review first on finite horizon problems. We have the general stochastic problem involving states, controls, and random disturbances. And given the current state, we go to the next state by selecting a control, and then the random disturbance picks a value, and we move to the next state, xk plus 1. And we also obtain a cost which is random because it involves wk. Now, the cost function is the sum of all the stage cost plus a terminal cost at the last stage. And we're interested in policies, sequences of functions that map states into controls. We assume that states are perfectly observed, and given a policy, it gives us the control to apply at that state. And for a given initial state, we want to minimize overall policies, this expected cost, which depends on the initial state and, of course, the policy. And the optimal cost function is the minimum overall policies, which depends, of course, on the initial state. And we are going to be focusing on finite horizon for the most part for the remainder of the course. For one thing, it's most convenient for algorithmic purposes. In particular, rollout that we're going to be focusing in greater detail sort of assumes a finite horizon. And if it's infinite, then we have to truncate it. However, in terms of implementation, in terms of conceptualization, nearly everything applies to infinite horizon as well. So again, let's review the dynamic programming algorithm. It produces the optimal cost of the tail subproblems starting at any state and stage. And it starts at the terminal cost, at the terminal stage, and goes backward with each iteration, computing the optimal cost of the tail subproblem of the current state given the optimal cost of the terminal cost of the following stage. And at the last step, we obtain the optimal cost of the finite horizon problem. And to obtain an optimal policy, we have to minimize in this expression, assuming that we have already computed j star k plus 1. Now, the problem with all this is it's very time-consuming. For challenging problems, it's totally intractable. And reinforcement learning deals with ways to simplify this computation and simplify the computation of an optimal policy. And a major part of reinforcement learning, perhaps the most important part of reinforcement learning, is approximation in value space, whereby instead of this J star, K plus 1, which is hard to compute, we use some approximation J tilde. And then once we have J tilde, then in real time, we do this minimizations at stage K. Given Xk, we minimize this expression, obtain U tilde K, which is the cost, the control that we apply. And there's also a multi-step version of this, which we're going to come to shortly, which involves, instead of solving a one-stage problem, solving a multi-stage problem of smaller horizon than the original. And the key question is, how do we compute J tilde? There are many different ways. Online rollout is one. Offline training using neural networks or other things is another possibility. Problem approximation, heuristics, and so on, as we have discussed. 90% of reinforcement learning revolves around how we compute this J tilde, and also perhaps how we do some approximations here so that this computation is not so onerous. Now, we're going to be focusing on finite horizon problems, but we have talked a lot in the previous lectures about infinite horizon problems and gotten insights and visualizations. So it's important to understand that a finite horizon problem can be transformed to an infinite horizon problem. So the algorithms and insights that we've gotten from infinite horizon can be applied to finite horizon. So how do we do this? In a finite horizon problem, we have n stages, and we have a state space and control space corresponding to each stage. X0 is the state space of the initial states. X1, capital X1 is the space of states X1, and so on. And we take, to construct the state space of the infinite horizon problem, we take the union of all these state spaces, and we also add a termination state, which we have to reach upon reaching the end of the horizon. And now, so this is the state space of the infinite horizon equivalent problem. The control space is obtained by looking at controls that are available at each state here. And the transition function, the system function, is the one of the finite horizon problem and takes us from X0 to X1, from X0, X1 to X2, and so on. So we have stacked up all the system functions into a big system function that gives you the one of the infinite horizon problem. So from some state here, we go to some state here according to the transitions that we have described, and so on. However, notice that these transitions go upwards, and within at most n steps, they reach a termination state where we stay at no cost. This is the end of the horizon. So now, if you look at the states that start the initial states at X0, in one step, we're going to be in X1. Another step is we're going to be at X2, and so on. After n steps, we're going to be at Xn, and then there is a transition to the termination state, the end of the horizon, at cost, this terminal cost. The intermediate transitions have costs of the, G0, G1, G2, and so on. So now if you eyeball this figure here, let's look at the optimal cost function of the infinite horizon problem. It gives you a value for every one of these states here, states in here, and so on. And it's very easy to see that the optimal cost of the infinite horizon problem, starting from these states here, is the same as the optimal cost of the finite horizon problem, starting at X0. The optimal cost of the infinite horizon problem starting from these states is J1 star of X1, J2 star, and so on. So the optimal cost of the infinite horizon problem is a stack of all these costs of K subproblems. And the optimal control, also the optimal policy of the infinite horizon problem, also gives you an optimal policy for the finite horizon problem. So there's a one-to-one equivalence here, and moreover, if you write the Bellman equation for the infinite horizon problem, there's one Bellman equation for every state, where we are in these spaces. And you'll see that it's exactly the dynamic programming algorithm for the finite horizon problem. So Bellman equation for infinite horizon is the n-stage dynamic programming algorithm for the finite horizon problem. And the interpretations we gave for Bellman's equation, like the Newton step and so on, they apply also to finite horizon with this transcription here. In other words, a Newton step on the Bellman equation of the infinite horizon problem is a Newton step on the dynamic programming algorithm of the finite horizon problem. It's more complicated. You can't visualize it, but it is there. Moreover, things like policy iteration can be applied to this infinite horizon equivalent and give you a policy iteration algorithm for the finite horizon problem. Policy evaluation followed by policy improvement, and then policy evaluation again, and so on. So all the theory for infinite horizon applies also to finite horizon. All the insights also apply. It's just that the finite horizon version is simpler because the infinite horizon problem here has a special structure. From all states, we get to the termination state and so on. Infinite horizon problems can be more general than that. However, all our insights from infinite horizon apply. That's the point that I want to make. Are there any questions about this diagram? Is it clear? Okay, so let's keep going. Let's talk about rollout and review it. Rollout is a special case of approximation in value space, a special J tilde. You have seen this before. I'm showing the multi-step look-ahead case, L-step look-ahead version, and minimization of the sum of the first L-step cost plus the future as measured by the cost function of some base policy. Okay, so that's distinctive about rollout. J tilde is the cost function of some base policy or some heuristic. And I'm going to be using these terms throughout: base policy and the policy obtained by look-ahead minimization. In other words, when you minimize here, you obtain UK plus sequence of news, and you apply the first UK and then throw out the rest, and that defines the rollout control and the rollout policy. So this rollout policy is a finite horizon policy. We call it the rollout policy to distinguish it from the base policy. And we're going to look at the various interpretations here. Of course, we have already gone through the Newton step interpretation that the optimal cost of the rollout, the cost of the function of the rollout policy is a result of a Newton step, starting from the cost function of the base policy, which is J tilde functions. But we are interested in establishing whether the rollout policy is better than the base policy in terms of its performance, and also look at variations of this algorithm here, where J tilde, instead of being the exact optimal, the exact cost function of a base policy, it may be an approximation to that, obtained, for example, by truncation and cost function approximation. So this is the broad landscape that we're going to be operating in, and we are going to focus particularly in the deterministic case. Let me say a few things about why rollout is going to be important for us. One of the roles of rollout, one of the one of the things that it accomplishes is that it provides options for cost function approximation, which are implementable. They're implementable in particular by simulation. If we want to find the J tilde value at some state, we simply simulate the base policy from that state, and this gives us, within a reasonable approximation, the value of J tilde at that state. So it's one option for cost function approximation, implementable online, but it's also another reason, which if you go back to the visualizations we covered, we did in the previous lectures, you'll see that it's a good option because it approximates the optimal cost from above. And approximations from above, if you recall, tend to be better from the point of view of stability, for example, and for other reasons. So that's one important reason why we like Rollout. Moreover, Rollout is a basic building block of the policy iteration algorithm. It is also very important. And Rollout is a single iteration of the policy iteration algorithm. And the main difference is that Rollout can be implemented online through simulation, but approximate policy iteration cannot. You have to use some kind of a neural network to represent the cost functions of the intermediate policies. There are also approximate variants of policy iteration, and Rollout again comes into the picture in those. Okay. So here's some of the nice things about Rollout and why we will consider it as important. It is the easiest to understand method and to implement in reinforcement learning. It's very straightforward, easy to see why, easy to understand why it improves on the base policy, and also to implement it is very easy. To implement Rollout on a given problem, it takes 2 days, let's say. But then to implement a more complicated method, such as an approximate policy iteration algorithm, it may take 2 months. There's a day and night change in the difference in the difficulty that it takes to the difficulty of implementing Rollout and some of the other reinforcement learning algorithms. Also, to make these other algorithms to work is another story, because Rollout is by far the most reliable method within this landscape of reinforcement learning. It works just about every time, okay? Once you take some care to avoid some pitfalls, then it works. It's very straightforward to make it work. That's far more than I can say about some of the other methods in reinforcement learning, like the Q-learning methods, DQN, TD methods. To make those work, you have to work very hard, and you also have to be lucky, because they don't always work. This one works almost always. The other methods do not. They're flaky, and you may be lucky to make them work on a given problem, but don't expect the success to be replicated with a broader context. Okay, Rollout is very general because it applies to deterministic problems, stochastic problems, finite horizon, infinite horizon, and it's very general. It applies to control problems, but in the context of model predictive and adaptive control. So that's another advantage. It relates to Newton's method. That's part of the theoretical underpinning of the method. It deals with all-line replanning. So if the problem changes on you as during decision making, then whatever new problem it encounters is just incorporated readily within the Rollout calculations. And this also is true in the context of adaptive control. It's a useful alternative to reoptimization, as we discussed in the previous lecture. It relates to model predictive control, as we have discussed in the previous lecture, and Rollout can also be used to improve the stability of various MPC schemes, as I discussed near the end of my lecture last time, but is also explained in greater detail in your class notes. Finally, truncated rollout can be combined with many of the other reinforcement learning methods, such as self-learning, learning, aggregation, and others, in two ways. Truncated rollout can use as terminal cost approximation whatever these other methods produce. Also, it can use as base policy for rollout some of the policies that are obtained, for example, by self-learning or Q-learning, so on. So all of this make it a good starting point to the field of reinforcement learning, and also a suitable subject for you to do term papers and mini research projects. If you are to implement some of the more sophisticated reinforcement learning methods for a term project, I suggest that you think twice, because it takes a long time, and it's a dicey proposition to make these methods work. On the other hand, if you have experience and confidence in some of the other methods like TD methods, Q-learning, and so on, then by all means go ahead. I don't want to restrict you from doing so. Okay, so now we're going to go into deterministic problems and rollout. Are there any questions? Okay, in deterministic problems, there's no W, there's no stochastic disturbance. So given the current state, when we apply a control, we know exactly the next state. It's given by some known function. And the cost is also deterministic. The cost function is what you obtain from a sequence of controls. We minimize overall control sequences, this expression, and we obtain something that depends on we obtain the optimal cost, which depends on x0. And now finite state problems, a finite number of states at each stage, are nice in the sense that they allow computation to go forward. Dynamic programming computation becomes feasible. But also they can be visualized, they can be depicted in a planar graph like this. I've gone through this before. Let me review it. This is a layered graph. There's one layer for each stage. Here, the circles correspond to states. And these are the initial states at stage 1, the x1 states, the x2 states, and so on. The terminal states, xn, and then there's an artificial termination node to which we can move with cost being equal to terminal cost. So nodes, the circles, correspond to states, and the arcs correspond to controls. More precisely, state control pairs, xk, uk. The start node of the arc is xk. The end node is what you end, the state that you end up after applying uk. So here at x0, you apply u0. This corresponds to this arc here, and you end up on a corresponding state x1. At x1, you apply q1, and that's represented by an arc that takes you to x2. And all the controls available at a given state are given by the outgoing arcs, correspond to the outgoing arcs, and so on. So for a typical trajectory of the system, you start at x0, you select an outgoing arc, which corresponds to a control u0, or end up at x1. Select another arc, go to x2, and so on. And we obtain a trajectory that ends up at the termination node. And if you add the costs of these arcs, you obtain the cost of the sequence of controls. And the sum of these costs can be viewed as the length. Okay, I forgot to mention that for every pair, xk, uk, there's a corresponding cost. So the transition from each one of these, for every pair of states corresponds to the has cost equal to given by gk of x, uk. So the overall cost of a trajectory corresponding to a sequence of controls is the length of the path, with the length of each arc being the cost of the arc. So this brings us to an important connection between finite state, finite horizon problems and shortest path problems of a special kind, acyclic shortest path problems of this type that we've shown here. It's also possible to show that shortest path problems, deterministic shortest path problems, can be approached by dynamic programming, again with a graph somewhat like this. So there's an equivalence here, but we're going to focus on the fact that finite state deterministic problems are shortest path problems of a special kind and can be solved as shortest path problems, either exactly or approximately. So let's give a couple of examples here. Deterministic dynamic programming problems arise very often in combinatorial problems, like the traveling salesman problem that we have discussed in the past. Here's another example, classical example, the n queens problem, whereby we want to place n queens on a chessboard that's n by n square, and we want to place the queens so that there's no pair that attacks each other. In other words, there's only one on each column, only one on each row, and only one on each diagonal. So here I'm showing the 4 queens problem. And the way to formulate this as a dynamic programming problem is to break down the decision, the overall decision of placing the n queens into a sequence of mini decisions. First, place the first queen in the first row, then place a second queen in the second row, and keep going. So we model this as a 4-stage problem, whereby we start at the empty board, the starting position. And here we have 2 decisions. Place the queen at this square, square 1, place it square 2. Now the other 2 decisions, another 2 decisions, placing the queen in square 3 and 4. But this gives us symmetric solutions. So there's no loss of generality in restricting ourselves to just these 2 possibilities from the starting board. Now, as long as we can place queens without reaching an impasse, or a solution for that conflicts, and queens attack each other, the cost of the transition is taken to be 0. However, once we reach a position like this, where it is impossible to place any queen in the 3rd row without attacking one of these 2 queens, then we call this a dead-end position. It cannot be part of a solution. And then we move to a termination state with cost equal to 1. So these are the 2 possibilities in the beginning. And then at this position, there are 2 possibilities. Place a queen here and place a queen here. We cannot place a queen over here, right? Because then there would be 2 queens will attack each other, cannot place. The only possibility to place queens without attacking the other queen is to put these 2. And from here, we can go we can place a 3rd queen. From here, we cannot place a 3rd queen, but this is a dead-end position also. And with cost 1, we go to the termination state. Finally, if you choose this branch here, then we can place, the only way we can place a queen without conflict is to put it on this square like this. And then the only square where we can place the 3rd queen is over here. And then we get a solution. So we have obtained a solution which corresponds to a path of cost 0. the paths that are not solutions correspond to cost 1. So what we want to do is find the shortest path in this graph of successive queen placements. Okay, so that's easy enough, but once you increase the number of queens, then very quickly the problem becomes intractable. And not intractable, but much harder to solve, because the number of positions explodes. So for example, 8 queens problem, there's something like 8 million or so positions that you have to consider. You go to 16 queens, it's astronomical. So anyway, people have been able to partially solve this problem, and it has been proved that it is possible to always find a solution for n equals 4 and higher. For n equals 2 and n equals 3, the problem does not have a solution. But for n greater or equal to 4, it does have a solution. The number of solutions also is an interesting question. How many solutions there are? For 8 queens problem, there's something like 90 solutions, 90 configurations. And some people have obtained the asymptotic number of solutions as n goes to infinity. There's been a lot of interesting mathematics, combinatorial mathematics around this problem. We're giving this problem here as an example of a combinatorial problem that's very difficult to solve exactly, and for which approximate solutions are more promising. And in fact, people have constructed approximate solutions that have solved very large n queens, approximate solution methods that have solved very large n queens problems. Okay, are there any questions about the slide? So now let's go to rollout. You have seen this figure before. We go one state at a time, and at the current state, we consider all possible next states, all possible controls, and all possible next states. And then we apply a heuristic, a base heuristic. It doesn't have to be a policy in deterministic problems. Just something that provides you, that completes this trajectory from xk plus 1 all the way to the end. And the cost of the heuristic from a state xk plus 1 is denoted by h of xk plus 1. And what we do in rollout is we compute Q factors. A Q factor for every control, and given by this expression, the cost of the immediate first stage transition plus the cost of the heuristic from the next state. And then we select the control with minimal Q factor. So we go to the next state and then do the same thing again. Consider all controls, run the base heuristic from there, and so on until we complete a trajectory. There are also multi-step look-ahead versions where we look multiple steps ahead and then apply the heuristic from the leaves of the tree of multi-step look-ahead tree that we have constructed. And an important question is whether a rollout is cost improving. In other words, the sequence that you obtain by rollout has a cost that's no worse than the cost of the base heuristic. There's no guarantee, because this heuristic can be anything. It can be a very stupid heuristic and maybe misguide you. So under what conditions on the base heuristic are we guaranteed to get cost improvement? Okay, let's do a couple of more examples. One example to which we're going to come back involves multiple vehicles moving on some graph and aiming to find aiming to perform some tasks that are located at particular points. And the objective is to perform these tasks in minimum time, with a minimum number of moves from the two vehicles to the two or whatever number there is vehicles. So this is a classical discrete optimization or combinatorial problem that is impossible, it's intractable for any number of vehicles and any substantial network here. It's completely intractable. And you can formulate, however, as a dynamic programming problem, where the state is the current position of the vehicles plus the position of the tasks that remain to be done, that have not been performed yet. And it's possible to try a heuristic like the one I'm showing here. Given the current location of the vehicles and given the current pending tasks, move each vehicle one step closest towards the closest task. In other words, each vehicle by itself and without coordination looks at the pending tasks, finds the one that is closest in terms of number of hops, and then moves one step along that minimum hop path. So that's the base heuristic. So let's see how by the way, the optimal solution here for this particular instance that I'm showing is to move vehicle 2 steps to node 7 and to move vehicle 1 3 steps to node 1. So there's a total of 6 moves, 3 for vehicle 1 and 3 for vehicle 2. 3 stages, 6 moves. However, let's see how the base heuristic performs. In the beginning, the vehicles are here. They calculate their closest pending task. And for vehicle 1, it is this one. And for vehicle 2, it's this one. So both of them move to this node. Then they are at the same location. So they're going to look at they're going to find the same closest tasks, so they're going to move together after that. And indeed, the base heuristic moves both vehicles over here. Then this has been done, this remains. So the closest route now is this one. So both of them move here, both of them move here, and both of them move here to perform the task. So it takes 5 moves for every vehicle for a total of 10, as opposed to 6, which is the optimum. And the reason for this is that the base heuristic does not involve any coordination between the vehicles. They don't tell each other what their moves are going to be. They just are independently and selfishly move in the direction that their own calculation dictates. Now let's see how rollout will work using this as a base heuristic. So at each stage, given the current pair of vehicle positions, consider all the possible pairs of moves from the current position. Now there are 4 pairs in this case here. 1 moves here, 2 moves here. 1 moves here and 2 moves here. 1 moves here and 2 moves here. And 1 moves here and 2 moves here. There are 4 pairs. Now for each one of these pairs, we run the base heuristic. We calculate the closest task and take 1 step in that direction. And then we compare the Q factors of the corresponding moves. So there are 4 Q factors to calculate here. And we select the move of minimum Q factor or minimum total vehicle moves. Okay, so now how will the rollout work here? It will consider 4 possible pairs. In particular, it will also consider this pair here. And then After that, it will calculate the corresponding the corresponding heuristic paths, and then it will select this one as being better. It's better than all the other pairs. So both of them are going to. So I'm sorry. I said it wrong. Okay. The good pair to consider is this one, this, and that. Then it will give you a Q factor that's equal to the optimal Q factor. So this is the one that's going to be selected, and then this is the one that's going to be selected, and so on. So by tracing the calculations here, you can show that the rollout algorithm finds the optimal solution. In this example, a total of 6 moves as compared to 10. So this is an example of cost improvement. And we're going to try to establish this property more rigorously. But also, it's an example of an important type of problem where simplifications are possible. It's a multi-agent problem. It involves 2 agents in this particular case, more agents in the more general case. And we are going to consider multi-agent rollout, which is different than the rollout I've shown here, and show later in a few lectures from now that multi-agent rollout performs much better than in terms of number of required moves and the number of required moves relative to this all at once type of rollout approach. Are there any questions here?
I have a question from a student here.
Okay.
Hello. So I wanted to ask, like in this case, when it says that the rollout finds the optimal solution. So I believe that when it chooses the first at the initial position, when it considers the pair where the vehicle 1 moves from 1 to 3 and 2 from point 2 to point 4, that's like the correct thing to choose. So as compared to this up pair, if we choose 1 to 4 and 2 to also 0.4, how does the base heuristic, what's the value of the base heuristic? Because if it only calculates the distance from the final position to the nearest reward, then it should still give lesser value for the wrong option, right? So that's why I thought I couldn't understand what the base heuristic is giving, the cost it's giving.
Okay. The optimal Q factor is going to correspond to this pair, which is the optimal pair. Now, what you're asking is what's going to happen if we consider the Q factor of this pair.
Correct, yes.
Then we consider the base heuristic from here for each of the two vehicles individually. So vehicle 1 is going to go here. That's the closest task. And vehicle 2 is also going to go here. That's the closest task. And basically, they're going to replicate the trajectory of the base heuristic, which is a cost of 10, a Q factor that costs you 10, whereas the Q factor corresponding to this pair costs you 6.
Okay, so what is the base heuristic calculating from any point? What's the function or what is it calculating?
It finds the closest task, okay, in terms of number of hops, and then moves each vehicle 1 step towards that task.
Okay, so
and that holds independently for both vehicles.
Okay, so will it also consider the other task after it finds the closest task for the total cost of that from there?
The base heuristic does not consider that at all. Only looks blindly. It's a myopic heuristic. It looks 1 step ahead only.
So I'm saying that when we are doing rollout for the Q factor is comprised of the current cost plus the heuristic from the possible solutions, right? possible
from the
states.
state where we land. Yeah.
Yeah. So in that case, if we consider the point 4 is where both vehicles land up. This is, I'm talking when it's rollout. So the current cost is 1 for each vehicle. And if we compute the heuristic from 4, then it should give 1 each, right? So total Q factor will be 4, correct? For this pair.
But the heuristic is run to the very end of the problem.
Yeah, so that's what I was asking. So heuristic calculates till till both the tasks or just the nearest task?
Right. Yeah. For each one for both tasks. Yes. So the heuristic is myopic, looks one step ahead, but it completes all the tasks. Okay. So the base heuristic from here goes to here, and then both of them go here, then both of them go here, and so on until completion.
Okay.
Yeah, the solution of this is outlined in some detail in your class notes. You may trace the steps there and just make sure that there's a comparison of all the 4 Q factors associated with the rollout.
Okay, sure. Thank you.
The base heuristic bases its decision one step ahead, but it still has to run to the entire trajectory, to the end of the horizon.
Okay, thank you.
Okay. Any other question? Okay, here's another example. This is a problem of some theoretical interest and some practical interest. It arises, for example, when you search through a maze from an entry point to an exit point, find a path of 3 passages to go through. We formulate it as in terms of a binary tree at some root, and up to a certain depth, n arcs, depth of n. And now some of the arcs in this tree are free and some are blocked. The ones that are blocked are the ones with a cross. So these are blocked and the others are free. And we want to find a path of 3 arcs from the root to one of the leaves here. That's the problem. So you can consider a base heuristic for this to be a greedy one and also myopic. Looks only one branch ahead. At a given node, if one outgoing arc is free, then you use it. If both arcs are free, then use the right arc. If both arcs are blocked, then okay, you can use also any one of them, but you're not going to get a free path this way. That's the base heuristic. So the way the base heuristic is going to work on this problem, this instance, at the root, both branches are free. So we move to the right, we choose the right of arc and go over here. But here, both arcs are blocked. So the base heuristic fails to find a free path in this particular instance. Now, the way the rollout is going to work is going to consider this move and that move, and then run the base heuristic from there. And the base heuristic from here chooses this arc and then this arc and finds the free path. Whereas from here, it does not. So the optimal Q factor is going to be obtained for this move here. So it moves over here and then it moves through and finds, in this particular instance, a free path. Now, this is not always guaranteed. It's not guaranteed that the rollout is going to find a free path, even if one exists. Dynamic programming, on the other hand, a full-fledged dynamic programming algorithm that starts from the leaves and goes backwards towards the root, assigning cost of 0 to a free arc and cost of 1 to a blocked arc will find a free path if one exists. However, the complexity of this dynamic programming algorithm is exponential because the number of leaves here at the last stage is 2 to the n, okay? And there are n steps to go through, so that's the complexity of the algorithm. On the other hand, the complexity of the greedy algorithm is O of n. There is a simple calculation to be done at every step, and there are n steps, so it's O of n. Now, the rollout examines at most n branches. No, I'm sorry. The rollout algorithm at each stage runs the greedy heuristic twice. So it's O of n times 2 for every stage. So it's O of n squared computation. Now, this is simple enough, a simple enough problem so that some analysis can be done. Like I said, there's no guarantee that the rollout algorithm or the greedy algorithm are going to find a free path if one exists. However, a probabilistic analysis can give the probability of finding a free path for both of these two algorithms, assuming that each arc is independently blocked with a given probability. Then if you calculate the probability that the rollout algorithm will find a breakthrough path, then it's larger, much larger than the probability of the greedy algorithm. And the analysis of this takes a couple of pages, but you can find the literature, and there's a reference in your class notes. The point I want to make here is that it's a qualitatively typical situation. Rollout improves the performance of the base heuristic quite a lot at the expense of a polynomial amount extra computation. Rollout does multiple calculations using the base heuristic. However, the number of calculations that it does is typically polynomial, so there's a polynomial expansion factor over the complexity of the heuristic. And this is an example that illustrates quite clearly this factor through analysis. This is qualitative. It's not rigorously established, but in practice, that's what happens. Okay, so now we've talked about this cost improvement property of rollout, and we're going to discuss it in some detail. First of all, it's not guaranteed automatically. Some special conditions have to hold in order to guarantee that the rollout policy has no worse performance than the base heuristic. The base heuristic can be anything. It can be arbitrarily stupid. So it can be designed in a way to trick the rollout algorithm to take wrong moves. So, however, there are some conditions that hold quite widely, and we can look into and also form the basis for making the rollout algorithm more robust and reliable. And these conditions are called sequential consistency and sequential improvement. And sequential improvement is more general than sequential consistency. But sequential consistency is easier to understand in some sense, and is also is relevant to stochastic problems. Okay, we say that the base heuristic is sequentially consistent if at a given state it chooses a control that depends only at that state and not on how we got to that state. In other words, the heuristic, if it goes to state xk, it generates the same trajectory regardless of how it got to xk. And another way to say this is to say that if the heuristic generates the sequence starting from xk, then once it moves to xk plus 1, it generates the tail of that sequence. And it's a definition of sequential consistency, and another way to phrase it is that the heuristic can be implemented as a legitimate dynamic programming policy, applying a control that depends only on the state that you're in. That generates the policy. Greedy heuristics are typically sequentially consistent. Like the nearest neighbor heuristic for traveling salesman problem, or the greedy heuristic for the multi-vehicle routing problem, they are sequentially consistent. You can show that. However, we're going to focus on a less restricted condition, which is a sequential improvement. So the purpose of sequential improvement condition is to imply this cost improvement property, namely that the cost of the rollout policy is less than the cost of the base heuristic. Here's the definition of sequential improvement. In the process of rollout, you calculate various Q factors. And at the given state that you are, there's also a cost generated by the base heuristic. And sequential improvement requires that the best heuristic Q factor is less than the cost of the heuristic at the state xk where you are at all xk. So when you are at xk, you have calculated the cost of the heuristic from there. And now you calculate the Q factors corresponding to various controls by adding the current cost plus the cost of the heuristic from the next state. And this is the Q factor of Qk. What this says is that there is a Q factor that's no worse than the cost of the heuristic from xk. Okay. And this you can check in various situations, and it guarantees, I claim, that there's cost improvement in this sense. So to understand this, let's look at this figure here. Okay. In rollout, we generate a sequence of states and controls. And let's say that we have reached the state xk. Let's interpret the sequential improvement condition. At xk, you can run the base heuristic and you have calculated this cost. Now, this is done in the process of reaching xk, because at xk minus 1, you have calculated all of these Q factors corresponding to the different controls. And the Q factor for the control that rollout has chosen is precisely equal to the cost of this transition plus this cost here. So as we reach xk tilde, we have calculated the cost of a trajectory, which we call the current trajectory at time k, which is the cost of up to here, and then followed by the cost of the base heuristic. Now, once we reach this point, we look at all possible controls, and then we calculate the Q factors. We calculate the Q factor of this control, we calculate the Q factor of other controls. And the cost of this part is the cost of the base heuristic from this state. And now, what does rollout do? It compares all these Q factors and finds the best one. And let's suppose that this is the best one with trajectory Rk plus 1. Then the sequential improvement condition says that the cost of this trajectory is better than the cost of this trajectory. The cost of Rk is greater than the cost of Rk plus 1. Why is that? Well, this is the cost of the minimal Q factor. And this is the cost of the Q factor corresponding to, I'm sorry, this is the cost xk over here. And this cost of this trajectory is that part. So we are given that this cost is better than this cost. Therefore, the cost of the trajectory, Rk, is greater than the cost of the trajectory RK plus 1 because the two of them share this common initial portion. So according to the sequential improvement property, the cost of RK is greater than the cost of RK plus 1. So the current trajectory, we call this the current trajectory. The cost of the current trajectory cannot get worse with every iteration. Now, R0 is the cost of the base heuristic starting from x0. Rn, on the other hand, corresponds to the trajectory of the rollout. Therefore, by applying this many times from 0 times 0 to time n, we obtain that the cost of R0 is greater than Rn. And this is the cost improvement. In other words, what we have here is a sequence of generated trajectories by rollout, these current trajectories, R0, R1, R2, and so on, and each is better or no worse than the preceding one if the sequential improvement condition holds, and therefore it implies what we want to prove. The other thing to note here is that sequential consistency implies sequential improvement. The reason is that under sequential consistency, the current trajectory is also corresponds to a Q factor that we apply. In other words, this is also part of the trajectory that we generate at xk, and here we choose the best trajectory. So since it's under sequential consistency, the base heuristic control is one of the controls that we minimize over. This condition holds. Okay, so this is a proof, and you can look over it. The main thing is that under sequential improvement, I have this monotonicity property of these trajectories, and I'd like to illustrate it with an example. So this is familiar. We've gone through this example before. It's a traveling salesman example involving 4 cities. And here's the matrix of intercity travel costs. We formulate this as a 4-stage dynamic programming problem. The black numbers here corresponding to the intercity travel costs. And at every stage, we select the next city to go to, start arbitrarily from A, go to AB, AC, or AD, and so on. And we will use the nearest neighbor heuristic that we have used in the past. And we can show that it is sequentially improving as well as sequentially consistent. And now we want to see these current trajectories and why they get improved at every step. So here's how the algorithm will work. At the initial state, we apply the base heuristic and generate the first trajectory by following the nearest neighbor. And the nearest neighbor heuristic generates this blue trajectory here. So that's the first trajectory corresponding to the base heuristic. Now, in the first step of rollout, we look at all these next city possibilities, and we run the nearest neighbor heuristic from each one. Okay, from here, the nearest neighbor heuristic is this one. From here, the nearest neighbor heuristic is this one. And here, it's, okay, I think it's this one here. We compare the total Q factor, the total cost, the Q factor of this move, and that move, and we find that this one is better. So now this is our current trajectory. This is R1, and it is better than R0. If you compare the numbers, I think this is 27. This one is 28. Now we are here, and we look at the 2 possible next cities. And then we run the nearest neighbor heuristic from each one, which is, okay, there's no choice here. And the optimal Q factor is obtained from this path here. And this gives us the new current trajectory, which is R2. So we started with R0, went through R1, and now R2 is even better. It has a cost of 13 relative to 7. So that's what this inequality show here. That's the key to understanding the cost improvement property of rollout. It generates current trajectories that are monotonically increasing, with the first one being the trajectory generated by the base heuristic, and the last one being generated by the rollout algorithm. Questions here? Okay, it's time to take a break, and we'll come back in 15 minutes, and you may ask questions about the first part of the lecture. Be back at 5:55. Are there any questions from the first half of the lecture? Okay, so now let's go into some variations of deterministic rollout. The first variation is simplified rollout algorithm. It is aimed towards economizing on the calculations of the standard algorithm. The standard algorithm involves calculation of all the Q factors at a given state. These Q factors may be a very large number. So ideally, we would like to reduce this number without losing some kind of the cost improvement property. So here's one way to do it, assuming the sequential improvement condition. Instead of applying the control that has minimal Q factor, use any control that has a Q factor less than the heuristic cost at the state that you are. In other words, when you are at xk, choose as rollout control any U tilde that has a Q factor less than the cost of the base heuristic starting from xk. And the idea here is to focus on a small subset of promising controls, find one that satisfies this condition in order to guarantee cost improvement, and in this way save lots of computation. As an example, I mentioned earlier the Wordle puzzle, the solution of the Wordle puzzle using a rollout approach. And in the Wordle case, the number of Q factors at every state is like 12,500, okay? It's a very large number, and to economize on computation, together with my students Sridhant and Amrita, we reduced the set of Q factors to something like 15, 20, 50, a very small subset, however intelligently chosen according to some heuristic preliminary calculation. And this was critical for being able to solve the problem in seconds as opposed to being able to solve the problem in hours, okay? So let's see how this condition here can serve as a substitute of the sequential improvement condition. It is actually very simple. What we're going to show is that the rollout policy under the simplifying algorithm operation has a smaller cost than the heuristic cost starting from any state. And the proof is exactly the same as for the proof under the full sequential improvement condition. this condition here is sufficient to guarantee that the current trajectory cannot get worse at every step. So we have that the current trajectory at time 0, which is the cost of the base heuristic, cannot become worse until the end, which gives us the cost of the current trajectory becomes the trajectory that's generated by rollout. So it's the same proof. It's just identifying the critical part where we can cut corners and using this condition instead of the minimum of this being less than h_k of x. Okay, here's another interesting variation. In many problems, there may be multiple heuristics that seem promising and that we would ideally want to use. It would be nice if we could use the right heuristic at the right part of the state space. So this variation allows us to do something like that. We combine several heuristics by constructing a super heuristic, one that at each state encountered runs all the heuristic and selects the best out of the trajectory produced. Considers all the Q factors of all the heuristics and then finds the best of all of them. Now, more formally, we can view the super heuristic as a different base heuristic for the rollout algorithm. And what we're going to show is that if all the heuristics are sequentially improving, then the same is true for the super heuristic. And for this, we have to verify the definition. Okay, we have capital M heuristics here. The typical one corresponds to little m, and the sequential improvement condition for the M heuristic is this one. This corresponds to the cost of the M heuristic from xk, corresponds to the Q factor corresponding to a pair xk uk, again for the M heuristic, and the sequential improvement condition is precisely what you see here. Now we take the minimum of both sides over M, over all the heuristics. And on the left, on the right, we get the minimum of this heuristic, which is precisely the super heuristic cost. On the right, we obtain the minimum over M of the minimum over controls. But we can interchange the order of minimization. First minimize with respect to U, and then minimize with respect to M. And then we observe that the super heuristic Q factor is precisely what you see here. Corresponds to the minimum Q factor over all the heuristics and over all U and X. So from here, the hypothesis, we get to this, and this is precisely the sequential improvement condition for the super heuristic. This is the minimal Q factor, and this is the minimum heuristic cost corresponding to heuristic. So this is very simple to prove and very, very useful. Are there any questions here? Okay, now let's try to go a little bit in great detail on the issue on the sequential improvement condition. I'm going to give you a counterexample where it's violated and the rollout algorithm performs worse than the base heuristic. So this example involves, very simple, involves two stages, an initial state x0, from which we can go to two other states, x1 star and x1 tilde, under control u0 star and u0 tilde. From x1 star, we can go to x2 star with this control, or we can go to this x2 tilde using another control, which has high cost. I'm reading this example so that it produces, so it's a counterexample to cost improvement. And If you go to x1 tilde, then there's only one choice. So let's assume that the optimal trajectory is this one. And part of the reason for that is that this transition here has very high cost. So this is the optimal trajectory. And let's assume that the Bayes heuristic chooses that optimal trajectory at the very first step. That's my choice for this example. And also assume that so we assume that the heuristic produces U0 star, U1 star at x0, and it chooses this one here at x1 star. So it's not sequentially consistent, and then and also not sequentially improving, as we will see. It changes its mind. When it starts here, the Bayes heuristic goes straight through to the top path. Once it reaches x1 star, it changes its mind and follows this part. If it starts here, it follows this transition. Now let's look rollout that uses the Bayes heuristic that I've shown here to construct a trajectory starting from x0. So what it does is it considers the two controls, considers this one and considers this one. And at this point, it follows the Bayes heuristic, which is this transition. And from here, the Bayes heuristic takes you here. So because this one has very high transition cost, the rollout selects this control. And then from here, it goes here. So it misses out on the optimal trajectory and generates a worse cost. The Q factor of U0 star, because of this transition, is larger than the Q factor of U to the 0. So the rollout algorithm selects U0 tilde and moves to the non-optimal next state. So in the absence of sequential improvement condition here, the rollout can deviate from already available good current trajectory and follow an inferior trajectory after that. Now, this suggests a remedy. Detect conditions like that, where we are off to veer onto a current trajectory that's worse than what you have, and follow the best current trajectory found so far, even if the rollout algorithm suggests following a different but inferior trajectory. So in other words, what I'm saying is have some way to detect that this trajectory is worse than this trajectory, my current trajectory, and then do not switch to go this way, but rather continue to go that way. And this is the idea of fortified rollout. It's a modification of rollout and can work even in the absence of sequential improvement. It restores the cost improvement property for Bayes heuristics that are not sequentially improved. And the idea is what I described in the previous slide. At each step, follow the best trajectory computed so far. So at the kth stage of rollout, we have this trajectory, which is fixed, the so-called permanent trajectory. And we have computed the best trajectory up to now, which takes us to this state and the right trajectory that you have here. Now, at this point, we apply rollout. We consider all possible controls, find the one that has minimal Q factor. It's this green choice here. And then we compare this, the cost of this, with the cost of the best trajectory that we have found so far. And if this green trajectory is worse than this red trajectory, we don't take this step as rollout suggests, but rather we take this step that maintains, that keeps us on the best trajectory. So let me describe here in terms of these bullets. In addition to the permanent trajectory, we store a tentative best trajectory, this TK bar here. And once we find the minimum Q factor choice, the U tilde K, we compare it to the tentative trajectory, and if it's more costly, then we accept then we reject this choice, and otherwise we accept it and we update the tentative best trajectory to be this green trajectory. So in other words, always follow the best trajectory we have found so far. And if rollout suggests different because there's a violation of the sequential improvement condition, still stick with the best trajectory that we have so far. And this restores the cost improvement condition and works so well in some problems where the sequential improvement condition may hold for most states, but there may be some states where it's violated that may throw off the rollout algorithm. So I'm going to give you an example of how this works in the situation we had earlier. Remember the problem. This is the optimal trajectory. However, the rollout compares this with this and prefers to go this way. And because of this high cost transition, the cost of this trajectory is higher than the cost of this trajectory. So in the fortified rollout algorithm, the steps are at the initial state, we store as initial tentative best trajectory the unique optimal trajectory that's generated by the base policy. In the first rollout step, we compute the Q factors of U0 star and U0 tilde by running the heuristic from X1 star and X1 tilde. And even though the rollout prefers U tilde 0 over U0 star, it is the fortified algorithm discards U tilde 0 in favor of U0 star, which is dictated by the tentative best. Then it sets the permanent trajectory to this and continues and finds the optimal solution. This is a simple counterexample of how the fortified algorithm works, how it corrects the deficiency, the potential deficiency of the standard rollout algorithm. Are there any questions about this example?
I have a question from a student.
Okay.
So in this example, does the heuristic also need to violate the sequential consistency property?
I'm sorry, could you speak a little louder?
Yeah, so does the heuristic also need to violate the sequential consistency property?
Sequential consistency.
Yeah, so for in this example, when it chooses U1 bar at X1 star, but
Yeah.
previously it, while computing from X0, it had chosen U1 star at X1 star. So which doesn't this also violate the sequential consistency property?
Yes, it does. if it violates sequential improvement, it violates sequential consistency by necessity. But you're right, you're exactly right. If it were sequentially consistent, then it will continue to choose U1 star after it moves to X1 star. But it is not sequentially consistent, and it chooses in particular this transition, and it also violates sequential improvement because it's a high cost transition.
Okay. Yeah, I understand. So a follow-up question is, can there be a heuristic which violates one of sequential consistency and improvement and not the other one?
Yeah, sure, of course, yeah. Well, I mean, it's possible that the sequential, okay, when you're asking if it's possible to violate sequential consistency, but satisfy sequential improvement, right?
Yes. And also vice versa. Can it do one and not the other?
Okay, this happens in a very important case. It happens, we haven't shown this, but it happens in MPC. I mentioned in the last lecture that MPC can be viewed as a rollout algorithm, particularly for the case where the heuristic drives the state of the system to zero. Now you can prove that this particular rollout algorithm involves that this particular heuristic is not sequentially consistent, but it is sequentially improving.
Okay.
So it's possible to have the weaker condition satisfied, but the stronger condition not satisfied.
So, but the other way it cannot happen, right? That it violates improvement but satisfies consistency. That cannot happen, right?
That cannot happen because sequential improvement is the stronger condition. In other words, sequential consistency implies sequential improvement, but not the other way around.
Okay. Yeah, got it. Thank you.
Okay. Okay, so let's go on to our last subject, last variation of rollout, which we call model-free rollout, for the case where you either don't know the cost function or you don't know the constraints of the problem. Now, you may not know it, but there's a computer that knows it, okay? By model-free, nothing is model-free in reinforcement learning. There's always a model, but we tend to call a method model-free if the model is inside a computer as opposed to being explicitly known via equations that you can visualize and understand. So let's consider this problem here, the general discrete optimization problem, involving a cost function that depends on this vector of components, u0 up to un minus 1. And each component is separately constrained. And we have discussed how to formulate this generic problem as a dynamic programming problem. We introduce a state at time k, the partial solution consisting of the first components up to time k. And then we select the next component, uk plus 1, and then we continue when we form a tree of partial solutions, this expanding tree. And then if we knew this cost function here, we could do dynamic programming algorithm and define the optimal solution at the initial starting point. And however, this is totally intractable. On the other hand, it's possible to use approximation algorithms, rollout algorithms in particular, because rollout algorithms do not depend on how complicated the state space is. It can be very, very large, but it always looks at one state at a time. So now let's look at this context. And the way rollout would work here is at the current partial solution, it looks at all the possible components that come next, that we call the k plus 1. And then runs a heuristic, right? A base heuristic through to the end, completes a solution, and then compares the costs associated with these complete solutions and picks the next component to be the one that has the minimum cost. We assume here there is a cost only at the very last stage. On the other hand, what happens if we don't know G and we don't know the constraints? Instead, we have a base heuristic, which, given a partial solution, it can compute all next controls and generate from each one a complete solution. So this is a heuristic that completes a partial solution, but it's sort of invisible to us on how it does it. It's hidden inside some computer. Now, the other question is, suppose we have these complete solutions generated by the heuristic, how do we compare them? How do we choose the best one? We don't know this cost function, but we assume that we have a human or software expert that can rank any two complete solutions without assigning numerical values to them. In other words, the expert can tell us, given all the solutions, which one is best. And he doesn't have to tell us how he does it, but all we care is which one is best out of the candidate complete solution. So this kind of scheme, where we use a heuristic that's hidden inside a computer and an evaluator of cost that's also hidden inside a computer without having expressions that are analytically available, it's just the same. It's no different. We have all we need. So all the ideas of deterministic rollout that we have discussed apply to this problem as well. Is this clear? Are there any questions? Okay, here's an example of which I had personal involvement. And there's a paper that together with collaborators we have published on arXiv a couple of years ago. And this involves an RNA folding application. Now, this is a classical and important problem in computational biology, and involves sequences, RNA sequences. Now, an RNA sequence is just a regular sequence of letters, okay, for nucleotide types. And there are 4 types, A, C, G, and U. And these types can pair with each other. A can pair with a U, C can pair with a G. So we have a sequence here of such letters, and some of them may pair. Now, depending on the pairing has to satisfy the constraint. Not only the constraints of A to U and C to G and so on, but also other constraints that these pairs in the sequence should not be crossing. There are a number of constraints that I'm not going to get into. Now, a given sequence, once you get the pairs in, then it becomes a complete folding. It's called a folding, and some foldings are more interesting than others. However, biologists do not agree what's the best folding. And instead, they have software that compare different pairings and tell you which one is the best according to the judgment of the software. Now, the software is not perfect. However, that's the best we have, and we can use it for building foldings. And here's what we have done in the way of rollout. We have a sequence, but not the pairings. And at each step, we go to one step forward in the sequence. We have already closed some pairings, up to that now. Some pairs may still be open, and we choose between three decisions. Either to close this pairing with some letter in the sequence that came earlier, or to open a pairing for pairing with future letters in the sequence, or to do nothing. So these are our controls. These are the states that we have gone through, and we want to pick one of these three decisions. And what we do is we have a base heuristic, which is a partial folder. What it does, given a partial folding, it completes the folding by making appropriate pairs according to its judgment. Okay. So the partial folding software give us complete foldings like that. And then we give this to an expert software that compares the complete foldings and gives the choice of best Q factor, either this decision, that decision, or that decision. So the base heuristic is here in this partial folding. And all we know about it is has some way that it generates a complete folding. And then two complete foldings are compared by the expert software. And in this way, we make decisions through Rollout. And there is no explicit cost function here. It is internal to the expert software. Besides, biologists cannot agree what's the best cost function here. Some people say that a minimum energy kind of criterion is the best, but this is disputed, and there is discussion about that. An interesting thing about this problem is that there is no optimal solution. However, there are useful solutions that Rollout can generate by using expert software, different types of expert software and different types of partial folding software. And we had some success with this algorithm here, but I'm not going to go into further detail. It's complicated. Treatment of constraints here is complicated. Actually, this application of Rollout connects with the constrained type of rollout that we're going to discuss in the next lecture. So I'm giving this as an indication of how one may apply Rollout in situations where the cost function is not known, but the details, there are quite a bit of details that I'm not giving here. You can read the paper here and also look into the material from the next lecture about constrained Rollout. Are there any questions here? Okay, about the next lecture. We're going to still stay with Rollout and look at the Rollout problems with multi-step look ahead. Everything we did today was single step look ahead, but in fact, multi-step look ahead in the context of Rollout is interesting because it is feasible. It's possible to do long look ahead in this context because the problem is deterministic. If the problem were stochastic, multi-step look ahead becomes more problematic. But with a deterministic problem, it's possible to do multi-step look ahead and gain something from that. So we're going to look at multi-step look ahead and put potential approximations to use within this context. Then we're going to look at another class of rollout algorithms that applies to constraint problems, where the constraints are not just instantaneous at the current stage on the control, but rather they involve trajectory constraints. Like, for example, the whole trajectory of states must be within some subset, some constraint subset. Then there is a modification of the rollout algorithm dealing with this type of problem. And this kind of modification also has a lot of applications in integer programming. And problems that people in industrial engineering and operations research worry about. And we're going to look at some problems like that in the context of constrained rollout. Your homework was due today, and I hope you're okay with all that. And there's going to be another homework that's going to be due in 2 weeks. And this is exercise 1.3 in your class notes. And it deals with a multi-agent problem. It's sort of a fun problem. It involves spiders and flies. It's sort of an extension of the example that I gave a few lectures back. And the multi-agent problem, we haven't fully covered the theory of multi-agent problems, but we've covered enough in the third lecture for you to be able to do this problem. If you have any difficulties, you can get in touch with me or with Jameson, but that's your homework. Have any questions? Okay, guys, we'll see you next week.